Hello and welcome to Investigative Math. This is the second video in this series on confidence intervals. In this video, we are going to develop an equation for the confidence to calculate the confidence interval of a certain distribution. I will be assuming some things that I went over in the last video, so if you're not familiar with terms like confidence interval or 95% confidence or things like that, I would highly recommend going back and watching the previous video, or else a lot of this stuff will probably not make very much sense. So we're going to start off. I'm just going to draw a bell curve, or try to. These are surprisingly difficult to draw. Okay, that's not fantastic, but it's okay. Down the center here, this is going to represent one of our sample distributions. Meaning, say we're dealing with heights, right? And you're dealing with the heights of people in the United States. So a sample distribution would be like if I took a sample of 100 people in the United States and took the average of their heights. And made a distribution out of their heights. So right here, down the middle, at our highest point, would be the mean of our distribution. Let's say that is 67 inches, right, which is like 5'7". And let's say that the standard deviation of this, the standard deviation of our sample distribution is, oh wait, I actually used the wrong thing. Our standard deviation is 2 inches. If you're not familiar with standard deviation, there's lots of other videos, lots of other statistics videos out there explaining standard deviation, but basically the gist of it is standard deviation is like a measure of spread. So let's say you had a standard deviation of 10, you would be much more likely to see people that are 77 inches tall than if you had like a standard deviation of 2, where you would be just as likely to see people that are 69 inches tall. So a smaller standard deviation basically means the data is closer together. A larger standard deviation means the data is more spread apart. So let's say we have this. Our mean is 67, and our standard deviation is 2 inches. So what we want to do in this video is try to figure out a formula to find the 95% confidence level. Actually, one second. We'll be needing that later. We're trying to find a 95% confidence level. So, pretty much, here's our sample mean. And when we're trying to find a confidence level, we're trying to be 95% sure that between our two values, right, between our two values is our population mean. So our population mean could be over here, it could be over here, but we want to create a region such that given a certain sample mean, we would be 95% sure that it would be there. So a pretty good way of doing that is to just include 95% of our bell curve in this distribution. So let's say we have a point right there and right here, and between these two values, on this interval, we have 95% of our bell curve. If you didn't know, the total area under a bell curve is 1. So if we have 95% of the bell curve shaded, that would be the same thing as containing 95% of our data. So that's a little bit of the jump. Again, that's for like a more basic statistical idea. If you haven't seen that, then I would highly recommend going to a different video, brushing up on that, and then coming back here. So, yes, we want to find whatever these two values are, right? We want to find this like A and this B, such that between these two values, we have 95% of our data. So this is what we're going to use. So you've probably heard of standard deviation, or actually we just talked about it, the standard deviation. Well, when you're dealing with confidence intervals, we have a slightly different idea, and that's called the standard error. And the standard error is very similar to the standard deviation, except for that it relates to our sample size as well. The sample size is very important. So the formula for standard error is the standard deviation divided by the square root of our sample size. And you can imagine why we would have to have this factor, right? Let's say that we took a sample of only one person. We would imagine that the standard error would be a lot bigger, right? If you sample one person, and let's say that that one person is, LeBron James, who is like 6'8" or something, right? Like 80 inches tall, then you would have to have a lot more, there would be a lot more variability in your graph. You would have to have a lot bigger interval to make sure that you would have the true mean, which let's say is, 5'8", which is 68 inches. So, in short, or like the general idea is, the bigger your sample size, the closer you're going to get to the true mean, right? Let's say you sampled 1,000,000 people, right? Let's say you sampled 1,000,000 people, right? The square root of 1,000,000 is 1,000, right? 2 divided by 1,000 is like 0.002. So our our standard error is now a lot smaller, which tells us that we are much more likely to have to have the population mean be close to our sample. So this is the formula we're going to use. Standard error equals our standard deviation divided by the square root of n. So in this example, let's say that we are sampling 25 people, because we are going to need that. Let's say we're sampling 25 people. So, I mean, this is nice, but we still have to find out whatever these values are. So, here's what we can do. Each of these values, this is going to be symmetric, by the way. Like A is the same distance from this as this is from B. We can model whatever A and B are as a certain number of standard errors away from the mean, and this is how we can do that. If we have 95% confidence, that means this area between A and B is 0.95, which means this area over here is 0.025, and this area over here is also 0.025, right? 1 minus 0.95 divided by 2 equals 0.025. So we can use our ideas from percentiles and z-scores to find out how many standard deviations, or how many standard errors away from our sample mean is A and B. So once again, this is a little bit of a more basic concept. If you haven't gone over this, before, I would highly recommend going back, but I will cover it briefly. So if you want to find how many standard deviations away from our sample mean B is, right? What you do is you set your set your mean equal to 0, and then say, well, if this area over here is 0.025, how many standard errors away would it have to be? So this is why I pulled up my calculator. We can go to Add Calculator, Menu 6, Distributions, and then number 3 is for inverse normal. Inverse normal, it takes a certain area and then tells you how many standard deviations away it is. So we have this thing, okay, so it tells us area. The area that it's asking for is actually the area to the left. So if we were trying to find our result for B, we would actually have to do 1 minus 0.025, which should be 0.975. So we'll put that in for our area. Mean of 0, standard deviation of 1. And this tells us that B is exactly 1.96 standard errors above our sample mean. That number that I just calculated is often called the critical value, and it's denoted as Z star. It's denoted as Z star. And so to find B, here's what you do. You take your sample mean, and then add Z star number of standard errors to your sample mean. So that's how you find B, and then A is a very similar thing, right? Because it's symmetrical, we can just subtract it in this case. So the way this is usually written as a confidence interval is our confidence interval is x bar, right, our sample mean, plus or minus our critical value times the standard error. And for this problem, in this case, right, standard error is equal to standard deviation divided by the square root of n. And so here is our formula for the confidence interval. It's going to be our sample mean plus or minus our critical value times standard deviation divided by the square root of n. So let's go ahead and calculate what this is actually going to be. So our sample mean is 67 inches, and then plus or minus z star, which we calculated to be 1.96, multiplied by our standard deviation, which is 2, divided by the square root of our sample size, like that. It's also be 67 plus or minus 1.96 times 2/5, right? That's 0.4. We can go ahead and calculate this. Oh, wrong thing. 67 plus that times 0.4, 67 minus that times 0.4. There we go. So we have this interval. So we are 95% confident, based on this sample, right, that the true population mean for the heights in this population is between 66.2 and 67.8. Okay, so I mean that's pretty powerful stuff, right? I mean we only have to sample 25 people, and from that, just from that, we can be 95% sure that our actual population mean is between 66.2 and 67.8. Granted, I did use a pretty small standard deviation. In reality, the standard deviation would likely be greater than this. Yeah, we likely be greater than this, but this is still some pretty powerful stuff. So that's about it. There's a lot to unpack here. So if you didn't catch everything the first way through, you could rewatch the video. If you rewatch it and you're like, okay, this doesn't make sense, or I think he misspoke here. I do make mistakes. I try not to make them in the videos, but it does happen sometimes. Don't be afraid to leave a comment. If you learned something, be sure to leave a like and subscribe, and I will see you in the next video.